Hello again, this is Mark Summers from Summers Technical Services. We're going to go over a final project and talk about filling out the spreadsheet and running the Solidworks simulation so we can correlate the principal stresses and von Mises stress that we learned about in Chapter 4 and do the hand calculations and then do the simulation and compare those two values, and they should match, and that'll give us high confidence that we've done the calculations correct and have the right stresses to figure out our failure theory based on von Mises stresses. So let's take a look at the material that you'll need. There's basically 3 pieces of information I've uploaded for you. There's 2 PDF files. One of them are these instructions here. I can drag this over here. There it is. So it goes through the different sections, hand calculations, and then a spreadsheet, and then doing the SolidWorks simulation. So I'll walk through these steps so you'll know what to do for the project. When you submit, on the final exam day, you'll submit your hand calculations. You'll just turn those in, start a class, and you'll submit your spreadsheet and your SolidWorks part model that you've set all the simulation up with via an email attachment. You don't have to send all the extra files that's created. All I need is a SolidWorks part model. It'll have all these settings you've created, and I'll be able to rerun it on my computer and check to make sure your numbers are all correct. So let's go through these one at a time. First thing, you're going to refer to this PDF document showing the details of the project. And so here's our part. It's a little bent tube. I've got the X, Y, and Z directions defined. And we're calculating, I've got 2 stress elements defined. For this particular assignment, you're going to be finding the stress values at this element A, which is at the top of the tube here as labeled. Do not do stress element B. We're going to do stress element A. So it's got the X, Y, Z values located. It's got a couple of forces out here, which makes it slightly different than our homework problem we did in Chapter 4. So you'll have 2 different moments created due to these 2 different forces, one of them in the X direction, one of them in the Z direction. You've also got unique values for A and B and the diameter, and you'll use those when you do your unique calculations. So let's go back over here and let's look at the spreadsheet. So when you start filling out your spreadsheet, you'll put your student number here. It'll automatically calculate these unique values for your geometry and the 2 forces you'll have. You'll type in, you'll calculate the C value. These are the shape properties. Calculate the C value, area, moment inertia, and polar moment inertia. And you're going to calculate the reaction moments at that stress element for a moment about x-axis, moment about y-axis, and the moment about the z-axis. Those are all, the units are all laid out there, so make sure you use the correct units. And now we're going to calculate all of the different normal stresses. It's a 3-dimensional stress problem, so we got sigma x, sigma y, and sigma z, 3 normal stresses. There's a total of 6 shear stresses, but we're only going to have to keep track of 3 of them because tau xy, as we've learned, is absolute value of tau xy is going to equal the absolute value of tau yx. Same thing with xz is the same as zx, absolute value wise, and then yz is the same as zy. So we got 6 stress values for shear stress, but we only need 3 unique values to define all of them. You'll notice some of these already have zeros in them. That's because it works out that those faces and those particular shear values are not existent due to the loads we have. So that'll help simplify what you're doing. So you're only going to calculate, you're going to type in the shape properties, you're going to type in your moments, and then you're going to do hand calculations to calculate sigma x due to F over A normal stresses. So this is normal stresses due to normal forces. This is normal stresses due to bending moments. And then you add those 2 numbers together to get the total sigma x value. You'll do that on all of these columns moving across. Here for tau xy, there is no shear stress due to shear forces at stress element A. There is going to be a shear stress on the x face in the y direction due to torque. You'll put that number there, and then this column here will just be adding those two numbers together. These last three, or last 6 entries are all zeros. Once you get all those values, then you'll use the equations I'll show you in a minute to calculate, or excuse me, you're going to calculate, you're going to get these from the model. And so let's go back to the PDF file and go through these steps. And let's see how far I got here. Come on. Here we go. So you're gonna. This is what I just talked about. Calculate normal shear stress at stress element A. Note some values are already zero. I've indicated those on the spreadsheet. Is what I just said. Enter those values and take the calculated values you did up in this section and just enter them into the spreadsheet. Now you're going to run the Solidworks simulation, and let's go through those steps now. Let's go pull up the Solidworks part model, and I'll go through those steps one at a time. So we're going to minimize this, and we're going to go open up the Solidworks model. File open. You're going to download this part model, and then you're going to save it with your student ID so I know whose it is. So first thing I do is do a file save as, put it in your U drive or whatever you put all your other files you've been working on all semester. Save as, I'll call mine 00. Alright, and I'm looking at the PDF file and going through these steps one at a time. First thing it says to do is to assign AISI 1020 steel. So I'm going to right click, edit material, and assign AISI 1020 steel, apply close. Next step says change the geometry for your A and B and D values. So you go tools, equations. You've got a global variable already done all this for you. Global variable A, you'll change to your A. Global variable B, those are the two dimensions. And then capital D is the diameter of that tube. So you'll change those values, say OK, and you will rebuild the model by hitting the red light, green light button up here, and that should make the model shape change based on your unique values. I've set up a couple of different isometric views. If you do a space bar, I've got a view called ISO new. That gives you the picture on the PDF file. Spacebar, you can do an ISO newer, and that'll let you look at it from the other direction if you want to. Probably the first thing you want to do is get rid of this annoying shadow floor reflection thing. So hit the color wheel, the display manager, and go to scene, lights, and cameras. I guess you right click on scene and then turn off floor reflection, right click again and turn off floor shadow. You don't have to do that, but it's annoying to me, so I always turn that off. So here's our ISO new. So looking at the instructions on the PDF file, change geometry, we did that. Okay, now we're going to put the loads in. So I want to put F sub X and F sub Z. And if I look at this picture right here again, drag this back over here so you can see it. So F sub X is going in the X direction, F sub Z is going in the Z direction on that end face. So I'm going to drag that out of the way, go get my spreadsheet, and look and see what my numbers are. And for student D, there's my numbers. Student 0, excuse me. And so it's got my force in the X direction of 1500 newtons. So I want to go start my study. So I'm back in SolidWorks. I want to say new study. It's going to default to a static study. I'll just say OK. I can give it a name if I want to. Now I've got a new tab down here that's starting the new static study. And I've got a different tree over here because now this is telling me about the simulation part of the model. And I'm going to just answer these questions left to right and then run the study. So the first question, it says apply material. I'll select that and I'll apply that material I just assigned in the model. It'll pull in all the applicable material properties. So I'll say apply close. So I've done that. Next thing is going to be the fixtures. I'm going to use the pull down, and I want to use fixed geometry on this back face where it's not going to be able to move in the X, Y, or Z direction. So I'll say fixed geometry. I'll spin this thing around, select this back face, and you can see I've got the arrows are telling me it's going to constrain that in the X and the Y and the Z direction. So I'll say OK. Give me another space bar and get back to my ISO new view. So I've done that. Now I'm going to put the loads on here. I'm going to pull this down, and I'm going to say I want to force. I want to force on this face. Excuse me. And I notice the force is not going in the right correct direction. It's assuming it was going to be normal to that face. I want it to go in the X direction. So I'm going to choose this button down here. It says selected direction. And I'm going to define the selected direction by clicking on this blue box here. And I'm going to choose the plane that is perpendicular to the direction I want the forces to go in, which is going to be this right plane. And when I select that, I can come down here and I can choose the value for the normal to that plane. So when I choose that, now that's going to it knows that I want to go in the X direction. And for my values on my spreadsheet, it says 1500 positive, which means it's going in the positive X direction. And that looks like that's correct, so I'll say OK. Now I need to do my F sub Z value. So I'm going to do the same thing. Pull down the loads advisor, click on force, select this face, and I got to define again a direction because I want it to go up, not into the face. So I'll say selected direction, and I want to choose a normal plane to that direction, and that normal plane is going to be this plane right here, the front plane. That'll define, I want to go normal to that plane to make it go up. So I'm going to again click this one down here, normal to plane. And I want to type in the number, which in my case is 1000. And it looks like it is going up. So I did that correct, it looks like. I'll say OK. Now that I've got the forces and I got my geometry correct, I'm just looking at the instructions here on the other screen. It says create mesh and run analysis. So I'm going to pull this. I'm not going to hit run this study. I'm going to pull this down and say create mesh. And I've got an option to choose the size of my finite elements. I can go all the way to the left. It'll give me a coarse mesh. That'll give me a not so good answer. I can but solve very quickly. I can swing it all the way to the right to make it a fine mesh. That makes the mesh much smaller. Tetrahedral elements are going to be much smaller, and it'll take a little longer to run, but it's going to give me a better answer. So I'm going to slide it all the way over, choose all the defaults, and say OK, and then see what kind of mesh size I get to see if my engineering judgment tells me that that's going to be a fine enough mesh to give me some reasonably accurate answers. And it's cranking out here. Hopefully it doesn't take too long. Alright, we'll zoom in here, and these are the little tetrahedrons. These are three-dimensional tetrahedral elements, and you can see I've got several elements across that diameter, and so I feel pretty good about the mesh size. So I'll go with that for now. Later on I might be able to make a finer mesh if I want to see if the answer is converging, but for now I'll use that. Now I'm going to go and save this thing so that I don't, in case it crashes, I can remember everything I've done up to this point. So it's saved, it's got all the settings in here. Now I'm going to say run this study, and it should pop up with a dialog box to give me some status. I'm going to hit the more button, and I can see the number of degrees of freedom, 250,000 degrees of freedom. It's got 100,000 nodes and about 67,000 elements. It's a pretty speedy computer, so I got a pretty good pretty quick results. Okay, so now we've done the analysis. Now we have to extract the results. And so I'm going to turn off this deformed result. It gives it in this exaggerated, deformed shape. I'm going to turn that off. And I'm going to start asking for the stresses I'm looking for. And so the first thing in my spreadsheet, what you're going to do is you're going to ask for the results from the stress analysis on the model, and you're going to check each one of the ones on your spreadsheet, and if they match closely, then you're going to have high confidence that you've got the right values. So let me open up the spreadsheet so I can check my numbers. I'll do a couple of them here so you kind of see how it goes. All right, I'm going to check sigma x on my model with my dimensions. So the first thing you're going to do is you're going to ask for the stress values that you want. So I'm going to right click on results, and I'm going to say define stress plot. And the first one in my spreadsheet is sigma x. And I'm going to just ask for it. I'm going to pull it down here. I'm going to say I want the normal stress in the x direction. And in my case, I want it to be in megapascals. So I choose megapascals, and I'll say OK. So now I've got, again, I got this deformed result I want to get rid of. What you'll do is you'll go through and do every one of the stresses we just talked about on the spreadsheet. You're going to get sigma x, sigma y, sigma z, tau xy, tau y. You're going to get all of them. So right click, define stress plot. You're going to define 6 different stresses to start with. You'll get 3 normal stresses and then 3 shear stresses. And you'll be able to check those values in your spreadsheet to make sure that all your values are correct in the spreadsheet. Those are all the kind of blue colored cells in the spreadsheet. So let's go. I'm not going to do them all here. You can do those on your own. Right now I'm on the normal stress in the x direction. Now I'm going to extract the value that I'm looking for. And so the first thing I'm going to do is go plot tools, section clipping. I want to take a section through the plane that I'm interested in, which in this case is the x face. So I'm going to do section clipping, and I've got the model set up so that plane is not the front plane. So I want to select that and clear it. I want to find the plane that goes through that face, and that's that plane right there, the right plane. When I do that, it shows me everything on this side of the plane, and it disappears everything on the other side. I want to flip that, so I want to hit the flip button over here. Now I've done section clipping right through that plane. This is the X face at stress element A. Stress element A is at the very top, right? Let's go look at the picture. Stress element A is, drag this over here, that point at the very top. So I want to probe it at the very top where stress element A is to check my numbers. Let's drag that over here, out of the way again. And so I've defined the section clipping. Now I'm going to look at this thing head on. So I'm going to do a space bar, and I'm going to click on this face here so I can look straight into that face. I'm going to zoom in here, and I want to now say plot tools probe. Now it's only showing me what's happening on that face, and stress element A is up here at the very top. So I'm going to zoom way in, and I want to select the very middle at the very top, and I get a number of 114.4, right? 114.4. My spreadsheet says 115.3. That sounds like the same number to me, so I'm happy with sigma x. And you're going to do that through all the other values, all the non-zero. You can check the zero values, and they should be pretty much at 0. So you're going to do that for all those blue cells in the spreadsheet. Make sure your numbers are right, because if your numbers are not right, that's how you'll lose points on the project. So I'm going to go back here. Okay, so now we get through the blue cells. Now it's time to go to the next step, which is, again, on these instructions. Let's go back to that sheet. And I'll zoom out of this thing a little bit. So we created a mesh, ran the analysis. We're going to extract the shear stresses from the results. That's what I just did. You're going to verify that you have the correct values in your hand calculations. Now we're on this step right here. You're going to extract the 3 principal stresses, sigma 1, sigma 2, sigma 3. You're going to extract those from the model, and you're going to enter those into a spreadsheet. We haven't talked about how to do these calculations because for three-dimensional stress elements, the calculations become much more complicated. So anything beyond a two-dimensional stress problem, the way you get these values normally is doing what we're doing now, which is an FEA stress analysis. So we're going to extract those three values from the results. We're also going to extract the von Mises stress, all from stress element A, and we're going to enter those into the spreadsheet. So there's three places, but sigma 1, sigma 2, sigma 3. There's two entries for the von Mises stress. One of them is the value from the FEA results. You're going to put that into the last column. Then, using principal stresses, you're going to calculate the von Mises stress at stress element A. And those numbers should match. So you got one, next to the last column is the calculated value for von Mises stress. You'll calculate using the values of sigma 1, sigma 2, sigma 3 from the model. Then you'll pull the results. You'll do your probe and find the von Mises stress at stress element A and put it in the last column. Once you verify those two are correct, that's what it says right here. Both should match. Put it in the spreadsheet, and then you're done. At that point, you'll save it, close it, send me the Solidworks part model, send me the spreadsheet, and then bring your hand calculations to class. Okay, so I think that describes all the things I'm looking for on the project. Go ahead and get started on it. You can stop by during office hours on Zoom or in person if you have any specific questions. Otherwise, get started on this, and then we'll see you next week at the final exam time. So until then, have a good day.